All right, let's talk about black holes. They're easily one of the most mysterious, most mind-bending things in the entire universe. But here's the thing. How much of what you think you know is just Hollywood, and how much is real science? Well, that's what we're going to do today. We're going to cut right through all the sci-fi myths and get to the heart of how these incredible things actually work, all based on the wild world of general relativity.
So first things first, let's just tackle the biggest myth right out of the gate. We've all seen it, this idea of black holes as these giant vacuum cleaners just roaming through space, sucking up everything in sight. But is that really what's going on? Well, the short answer is a big fat no. So yeah, that whole cosmic vacuum cleaner idea, it makes for a great movie scene, but it's just not how it works. Black holes aren't out there sucking things up from light years away. The truth is, honestly, way cooler. What they're really doing is bending and warping the very fabric of space and time itself. So objects aren't being pulled in, they're just following the super curvy road that the black hole has laid out for them. Now, if you want the official, scientific definition, the one straight from Einstein's playbook, it's even crazier. A black hole is basically a spot in spacetime where gravity is so unbelievably strong that once you pass a certain point, there's no getting out. Nothing. And I mean nothing, not even light, the fastest thing in the universe. Okay, so where do these things even come from? Well, for the most common kind of black hole, the origin story is seriously epic. It all starts with the death of a truly massive star. You see, for most of its life, a giant star is in this perfectly balanced cosmic tug of war. Deep in its core, nuclear fusion is creating this insane outward pressure, constantly pushing everything out. At the very same time, the star's own humongous gravity is trying to crush everything inward. It's a standoff that can last for millions of years. But that balance can't last forever. Eventually, that star starts to run out of fuel. The fusion furnace in the core sputters and dies, and that outward push just vanishes. And with nothing holding it back, gravity wins, and it wins in the most spectacular fashion imaginable. The core collapses in on itself catastrophically, crushing itself down into a point of almost infinite density. Now, not just any star gets to do this. You have to be a real heavyweight. For a black hole to form, the core that's left over after the star collapses has to be more than 3 times the mass of our own sun. That's the magic number. Only then is gravity strong enough to just overpower everything else and form a black hole. So, we have a black hole. Now for the fun part. Let's imagine we're taking a trip right up to its most famous feature, the edge, the point of no return. This edge is called the event horizon. And it's so important to get this. It's not a surface. You couldn't, touch it or stand on it. It's just a line in space-time. But once you cross it, the game is over. The way space-time is bent means that every single path you could possibly take leads in one direction, down, toward the center. Escape is literally impossible. There's this great line that sums up general relativity perfectly. It basically says that mass tells space-time how to curve, and that curve tells matter how to move. And that's exactly what's happening here. You're not being pulled in by a force. You're just following the path of least resistance through a part of the universe that's been bent into an extreme one-way street. It's geometry, not suction. And here's where things get really, really weird. I mean, truly strange. Because what you'd see happen depends entirely on where you're watching from. To us, way back at a safe distance, we'd watch something fall in and it would look like it's slowing down and down and down. Its light stretching out and getting redder until it looks like it's just frozen in time, right at the edge, forever. But for the thing actually falling in, whoosh, it would just cross the event horizon in a totally normal amount of time, probably not even noticing anything special at that exact moment. How crazy is that? So what's waiting at the very center? What's at the bottom of this cosmic well? Well, according to our best theories, it's something called the singularity. This is where all that mass, all that stuff from a giant star gets crushed into a point with zero size, an infinitely small point. And right there, gravity becomes infinite. And all the laws of physics that we know and love just break. They stop working. It really is the ultimate mystery. Which, of course, brings up a really good question. If these things trap light and are totally invisible, how in the world do we even know they're out there? How do you find something you literally cannot see? While the trick is, you don't look for the black hole itself, you look for the chaos it causes around it. We look for its massive gravitational footprint on everything nearby, like the super hot stuff swirling around it, the way it bends light like a lens, and even the incredible shadow it casts. Think about it. When gas and dust get close to a black hole, they don't just fall in. They get whipped into this massive, spinning, flat disk of material called an accretion disk. And the friction in this disk is so intense, it heats up the matter to millions of degrees. It glows so brightly with X-rays and radiation that sometimes this little disk can actually outshine its entire home galaxy. And if that wasn't enough, that spinning disk can do even more incredible things. The powerful magnetic fields that get tangled up in there can act like a cosmic cannon, shooting out enormous jets of particles that travel at almost the speed of light. And these jets can blast out for thousands of light years, way, way beyond the galaxy itself. So it's pretty clear these aren't just passive, dead objects, right? They are active, powerful forces shaping the cosmos. So let's zoom out a bit and look at the bigger role they play in the universe. We've mostly been talking about what are called stellar mass black holes, the ones that come from dying stars. But there's a whole other category, the supermassive black holes. We're talking absolute monsters here, millions, sometimes billions of times the mass of our sun. And we find them lurking in the heart of pretty much every big galaxy, including our own Milky Way. And this really is the biggest takeaway. Black holes are not just cosmic destroyers. They're actually fundamental engines of the universe. Those supermassive ones at the centers of galaxies, they are absolutely crucial to how galaxies form and grow over cosmic time. They're not just wrecking balls, they're architects. They really seem like they'd be permanent, right? These eternal monuments to gravity. But what if they're not? What if even a black hole can die? And this question takes us right to the cutting edge of physics. The legendary Stephen Hawking, by brilliantly mixing quantum mechanics with general relativity, predicted that black holes aren't perfectly black. He theorized that they can actually leak a tiny bit of energy back out into space, something we now call Hawking radiation. This means that over unimaginable amounts of time, trillions upon trillions of years, black holes might just slowly evaporate. We haven't seen it happen yet, but it's this mind-blowing idea that points to the deepest mysteries we're still trying to solve.